Look up at the night sky on a clear evening, away from the lights of the city, and you might see a faint, glowing river of light stretching across the darkness. The ancient Greeks saw this celestial band and called it Galaxia's Kyklos, the Milky Circle. The Romans named it Via Lactea, the Road of Milk. We know it simply as the Milky Way, and it is our home on the grandest scale imaginable. Tonight, we're going to journey through 100 remarkable facts about our galaxy, piecing together the story of this cosmic island that has cradled our solar system for over 4.5 billion years. So settle in, relax, and let's begin our voyage through the starlit spiral we call home. The grand design. Our Milky Way is a barred spiral galaxy, which means that if you could somehow step outside and view it from above, you'd see elegant spiral arms curving outward from a bright central bar of stars. This cosmic pinwheel stretches an almost incomprehensible 100,000 light-years from edge to edge. To put that in perspective, light traveling at 186,000 miles per second would take 100,000 years to cross from one side of our galaxy to the other. Within this vast expanse, somewhere between 200 billion and 400 billion stars call the Milky Way home. That's more stars than there are grains of sand on all the beaches of Earth, each one a sun in its own right, many with their own families of planets orbiting in the darkness. The Milky Way isn't flat like a dinner plate, though. It has thickness to it, bulging at the center and tapering toward the edges. At its heart, the galactic bulge rises about 10,000 light-years thick, while out in the spiral arms where we live, the disk thins to just 1,000 light-years from top to bottom. Our solar system makes its home in one of these spiral arms, specifically a minor arm called the Orion Arm, or sometimes the Orion Spur. We're located roughly 26,000 light-years from the galactic center, about halfway out toward the edge. It's a comfortable spot, neither too close to the violent center nor too far out in the sparse outer regions. From our vantage point here on Earth, the Milky Way appears as that band of light crossing the night sky because we're looking through the flat disk of the galaxy. When we gaze up at that misty river of stars, we're actually looking edgewise through billions of distant suns, their combined light creating that soft, luminous glow that has captivated humans since the beginning of time. The entire galaxy, with all its stars, planets, gas clouds, and mysteries, is in constant motion. Our solar system orbits the galactic center at approximately 514,000 miles per hour. It sounds impossibly fast, yet at this speed, it still takes us about 230 million years to complete one full orbit around the galaxy. The last time we were in this exact position in space, dinosaurs were just beginning to walk the Earth. As we spin through space on this grand carousel, our galaxy itself is also moving through the universe. The Milky Way is approaching the Andromeda galaxy, our nearest large galactic neighbor, at about 250,000 miles per hour. Don't worry though, these two galaxies won't collide for another 4 billion years or so. At the very heart of our galaxy, hidden behind clouds of dust and gas, lies something both fascinating and terrifying, a supermassive black hole called Sagittarius A star. This cosmic monster has a mass equal to about 4 million times that of our Sun, sitting like a dark throne at the center of our galactic kingdom, holding everything in its gravitational embrace. The architecture of light. The Milky Way's spiral arms aren't just beautiful patterns in space. They're active stellar nurseries, regions where the raw materials of creation come together in cosmic clouds. These spiral arms contain most of the galaxy's star-forming regions, places where hydrogen gas and cosmic dust collapse under their own gravity to ignite new suns. The arms themselves aren't permanent structures made of the same stars, but rather density waves that move through the galaxy like ripples on a pond, compressing gas and triggering star formation as they pass. Our galaxy weighs approximately 1.5 trillion times the mass of our Sun. But here's something remarkable: most of that mass isn't in stars at all. The visible stars, planets, and gas clouds that we can see only account for about 10 to 15% of the galaxy's total mass. The rest is dark matter, an invisible substance that we can't see directly but know must be there because of its gravitational effects on everything around it. It forms a vast halo around our galaxy, extending far beyond the visible edges of the Milky Way's disk. The stars in our galaxy aren't all the same age. In fact, the Milky Way has had a long and complex history written in the ages of its stars. The oldest stars in our galaxy, found primarily in the galactic bulge and in globular clusters that orbit above and below the galactic disk, are approximately 13.6 billion years old. That means they formed less than 200 million years after the Big Bang itself. These ancient suns have witnessed nearly the entire history of the universe. Speaking of globular clusters, the Milky Way is surrounded by about 150 to 200 of these beautiful spherical collections of stars. Each globular cluster can contain hundreds of thousands of stars packed into a region just 100 to 200 light-years across. They orbit our galaxy like cosmic beehives, following elliptical paths that take them high above and below the galactic plane. Looking at a globular cluster through a telescope is like looking back in time, seeing stars as they existed in the ancient universe. Between the stars, space is not truly empty. The Milky Way contains vast clouds of gas and dust called nebulae, and within these clouds lies the raw material for future generations of stars. The galaxy contains enough gas and dust to continue forming new stars for billions of years to come. These interstellar clouds are where chemistry happens on a grand scale, where simple hydrogen atoms combine and recombine, where the heavier elements forged in the cores of ancient stars mix with the primordial gas of the early universe. Every star you can see with your naked eye from Earth belongs to the Milky Way. In fact, with rare exception, they're all relatively close neighbors in cosmic terms. Most naked eye stars are within 1,000 light-years of us, a tiny fraction of the galaxy's full extent. The most distant star you can typically see without a telescope is V762 Cassiopeia, a variable star about 16,000 light-years away. Everything else is simply too far and too dim for our eyes alone. The Milky Way isn't alone in its corner of the universe. It's the dominant member of what we call the local group, a collection of more than 50 galaxies bound together by gravity. Most of these are small dwarf galaxies, but the group includes 3 large spiral galaxies, our Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Together, these galaxies span about 10 million light-years of space. Among our closest galactic companions are the large and small Magellanic Clouds, 2 irregular dwarf galaxies visible from the southern hemisphere as fuzzy patches of light. The Large Magellanic Cloud lies about 160,000 light-years away, while the Small Magellanic Cloud is roughly 200,000 light-years distant. These small galaxies orbit the Milky Way, and over millions of years, streams of gas have been pulled from them, connecting them to our galaxy in a vast, invisible bridge of hydrogen gas. A galaxy in motion. The center of our galaxy is an extraordinary place, far different from the relatively calm neighborhood where Earth resides. The galactic center is a crowded, chaotic region where stars are packed so densely that the night sky, if viewed from a planet there, would be ablaze with thousands of stars brighter than Venus appears from Earth. In some regions near the center, stars are only light weeks apart, compared to the light-years of separation we experience in our solar neighborhood. It's a place of intense radiation, powerful magnetic fields, and violent stellar interactions. The Milky Way's disk isn't perfectly flat. It's actually warped, like the brim of a hat that's been sat on, twisting upward on one side and downward on the other. This warp becomes more pronounced toward the outer edges of the galaxy and is likely caused by the gravitational influence of our satellite galaxies, the Magellanic Clouds, tugging on the outer disk as they orbit around us. The warp means that the disk can deviate by as much as several thousand light-years above or below the main plane. Within our galaxy, stars are born at a steady but spectacular rate. The Milky Way produces approximately 3 new stars every year. That might not sound like much compared to the hundreds of billions already shining, but it means that over the course of human history, tens of thousands of new suns have ignited in the stellar nurseries scattered throughout the spiral arms. Each of these newborn stars emerges from collapsing clouds of gas and dust, some forming alone, others in great clusters containing hundreds or thousands of siblings. The central bar of the Milky Way, that elongated structure of stars running through the galactic core, is about 27,000 light-years long. This bar isn't stationary but rotates like a cosmic propeller, spinning faster than the spiral arms around it. The bar plays a crucial role in the galaxy's evolution, channeling gas from the outer regions toward the center, feeding star formation and possibly even feeding the supermassive black hole that lurks at the very heart of the galaxy. Our galaxy hasn't always looked the way it does today. The Milky Way has been built up over billions of years through a process called galactic cannibalism. Throughout its history, our galaxy has consumed dozens of smaller galaxies, absorbing their stars and incorporating their mass into its own structure. Even now, the Milky Way is in the process of devouring several dwarf galaxies. We can see the remnants of these ancient meals in streams of stars that trace the orbital paths of galaxies long since destroyed. The disk of the Milky Way contains distinct populations of stars that tell the story of the galaxy's chemical evolution. Astronomers divide stars into two main populations. Population 1 stars, like our Sun, are relatively young and metal-rich, found primarily in the spiral arms. Population 2 stars are older and metal-poor, found in the halo and bulge. When astronomers say metal, they mean any element heavier than hydrogen and helium. These heavier elements were created in the cores of earlier generations of stars and scattered into space when those stars died, enriching the gas clouds that would form the next generation. The rotation of the Milky Way reveals something puzzling. When astronomers measure how fast stars orbit at different distances from the galactic center, they find that stars in the outer regions are moving much faster than they should be based on the visible mass of the galaxy. This is one of the key pieces of evidence for dark matter. Without this invisible mass providing extra gravitational pull, the outer stars would be moving too quickly and should have been flung out into intergalactic space long ago. Instead, they remain bound to the galaxy, held in their orbits by matter we cannot see. The Milky Way has several distinct spiral arms, each with its own name. The two major arms are the Perseus arm and the Scutum Centaurus arm. Between these lie the minor arms, including our own Orion arm, as well as the Sagittarius arm and others. These arms aren't completely separate structures but rather regions of higher density where stars, gas, and dust concentrate. Material flows in and out of these arms as it orbits the galaxy, sometimes passing through an arm, sometimes finding itself in the space between. If you could somehow observe the Milky Way across different wavelengths of light beyond what our eyes can see, you'd witness an entirely different galaxy. In infrared light, we can peer through the dust that blocks visible light, revealing the warm glow of stellar nurseries and the dense concentration of stars at the galactic center. In radio waves, we can map vast clouds of hydrogen gas that trace the spiral arms. In X-rays, we see the violent, high-energy universe, exploding stars, matter being torn apart near black holes, and the million-degree gas that fills the space between stars. Each wavelength reveals another layer of our galaxy's complex and beautiful nature. The fabric of stars. The space between stars in our galaxy isn't as empty as you might imagine. The interstellar medium, as astronomers call it, is filled with incredibly thin gas and dust. On average, there's about 1 atom per cubic centimeter in interstellar space. That's a vacuum far better than anything we can create in laboratories on Earth, yet across the vast distances between stars, this tenuous material adds up. The total mass of gas and dust in the Milky Way equals billions of solar masses, enough raw material to continue making stars for billions of years into the future. Our Sun is actually quite typical among the stars of the Milky Way. About 75% of the stars in our galaxy are red dwarfs, small cool stars less massive than our Sun, while only about 7% are stars like the Sun or more massive. The most massive stars, the brilliant blue giants that can weigh 50 or even 100 times as much as our Sun, are incredibly rare, perhaps only 1 in 10 million stars. Yet despite their rarity, these massive stars shine so brilliantly that they dominate the visible appearance of spiral arms and star-forming regions. The Milky Way is surrounded by an enormous corona of hot gas extending hundreds of thousands of light-years into space. This galactic corona is incredibly hot, reaching temperatures of millions of degrees, yet it's also extremely diffuse, with densities far lower than the best vacuum we can create on Earth. This superheated halo contains a significant amount of the galaxy's ordinary matter, and it serves as a reservoir, slowly cooling and falling back into the disk to fuel future generations of star formation. Within the Milky Way, stellar explosions called supernovae occur roughly once every 50 years on average. These catastrophic deaths of massive stars briefly shine with the light of billions of suns, and they play a crucial role in the galaxy's evolution. Supernovae create and disperse heavy elements throughout the galaxy, enriching the interstellar medium with the carbon, oxygen, iron, and other elements necessary for planets and life. They also generate powerful shockwaves that can trigger the collapse of nearby gas clouds, sparking new waves of star formation. The energy from supernovae helps regulate star formation throughout the galaxy, creating a delicate balance between creation and destruction. The Milky Way's magnetic field, though incredibly weak compared to a refrigerator magnet, extends throughout the entire galaxy, threading through the interstellar medium like an invisible web. This galactic magnetic field influences the motion of charged particles and cosmic rays, channels the flow of gas in the spiral arms, and helps shape the clouds where stars are born. The field is generated by the combined motions of charged particles throughout the galaxy, creating a complex, ever-shifting magnetic landscape. Near the center of our galaxy, there exists a region known as the Fermi bubbles, two enormous lobes of high-energy gamma rays extending 25,000 light-years above and below the galactic plane. Discovered in 2010, these mysterious structures may have been created by a massive burst of star formation or perhaps a period of intense activity from the central supermassive black hole millions of years ago. The bubbles are still expanding, and their edges mark the boundaries where material from the galactic center collides with the surrounding halo. The concept of the galactic habitable zone suggests that there are regions of the Milky Way more conducive to life than others. Too close to the galactic center, and the high density of stars, intense radiation, and frequent supernovae would make life difficult to sustain. Too far toward the outer edge, and there might not be enough heavy elements like carbon, oxygen, and iron to build rocky planets and complex chemistry. Our solar system sits in what many astronomers consider the Goldilocks zone of the galaxy, far enough from the dangers of the center but close enough to have benefited from billions of years of stellar enrichment. The oldest known star in the Milky Way, catalogued as SMSSJ 031300.36-670839.3, is estimated to be around 13.6 billion years old, formed when the universe itself was less than 200 million years old. This ancient star contains almost no heavy elements, born from gas that was nearly pure hydrogen and helium from the Big Bang. Studying such ancient stars is like stellar archaeology, giving us a window into the conditions of the early universe and the first generations of stars that ever existed. The Milky Way doesn't rotate like a solid disk. Instead, different parts rotate at different speeds, a phenomenon called differential rotation. Stars closer to the galactic center orbit faster than those farther out, though not as much faster as you might expect from the visible mass alone. This differential rotation causes the spiral arms to wind up over time, and it creates shear forces in the interstellar medium that can compress gas clouds and trigger star formation. It's one of the many dynamic processes that keep our galaxy alive and evolving. Cosmic neighborhoods. The disk of the Milky Way is actually composed of two distinct parts, the thin disk and the thick disk. The thin disk, where most of the galaxy's stars reside, is about 1,000 light-years thick and contains younger stars, gas, and dust. The thick disk lies above and below it, reaching about 3,000 to 4,000 light-years in thickness, and is populated by older stars with different orbital characteristics. These two disks likely formed at different times in the galaxy's history, with the thick disk being older and the thin disk representing more recent star formation and galactic evolution. Within the Milky Way, stars aren't distributed randomly but often form in groups. Open star clusters, collections of dozens to thousands of stars born from the same molecular cloud, dot the spiral arms. The Pleiades, visible to the naked eye as a small fuzzy patch in the constellation Taurus, is one of the most famous open clusters, containing several hundred stars that are all siblings, born together about 100 million years ago. These clusters gradually dissolve over time as gravitational interactions with other stars and giant molecular clouds slowly pull the members apart, sending them on their separate journeys through the galaxy. The Milky Way contains vast structures called molecular clouds, the largest of which can be millions of times more massive than our Sun and stretch across hundreds of light years. These cold, dark clouds are the wombs of stars, containing dense concentrations of hydrogen molecules, along with traces of other molecules including water, ammonia, and even complex organic compounds. The most massive molecular clouds in our galaxy can give birth to thousands of stars at once, creating the brilliant star clusters and associations that illuminate the spiral arms. Our galaxy has experienced several major merger events throughout its history. Evidence suggests that about 10 billion years ago, the Milky Way collided with and absorbed a dwarf galaxy that astronomers have named Gaia Enceladus. This ancient collision delivered billions of stars to our galaxy and likely triggered intense bursts of star formation. The stars from Gaia Enceladus now populate the stellar halo, their unusual orbits marking them as immigrants from another galaxy, remnants of a cosmic merger that happened before our solar system even existed. The metallicity of stars in the Milky Way increases gradually from the halo to the disk and is highest in the central regions. This gradient tells the story of the galaxy's chemical evolution. The oldest stars, born from nearly pristine primordial gas, contain very few heavy elements. With each generation, supernovae and dying stars released more heavy elements into the interstellar medium, enriching the gas that would form subsequent generations of stars. Our Sun, born about 4.6 billion years ago, is relatively metal-rich, a testament to all the stellar generations that came before it. The Sagittarius dwarf elliptical galaxy, discovered in 1994, is currently being torn apart by the Milky Way's gravitational forces. This small galaxy is passing through the plane of the Milky Way's disk, and over hundreds of millions of years, it has been stretched into long streams of stars that loop around our galaxy multiple times. These stellar streams are like cosmic archaeology, allowing astronomers to reconstruct the orbits of satellite galaxies and understand how the Milky Way grows by consuming its smaller neighbors. Within the galactic disk, there are regions known as stellar voids or gaps, areas with notably fewer stars than expected. These gaps may be created by the gravitational influence of the spiral arms, which can clear out certain orbital zones, or they might represent the scattered remains of past close encounters with satellite galaxies. The structure of the Milky Way is far from uniform, filled with subtle patterns and irregularities that reflect its complex and dynamic history. The Milky Way's escape velocity at the Sun's location is approximately 550 kilometers per second. This means that any object, whether a star or a spacecraft, would need to be traveling faster than this speed to break free from the galaxy's gravitational pull and journey out into intergalactic space. A few hypervelocity stars have been discovered moving fast enough to eventually escape the Milky Way, likely flung out at tremendous speeds by close encounters with the supermassive black hole at the galactic center or by the explosive destruction of binary star systems. The vertical motion of the solar system takes us above and below the galactic plane in a gentle oscillation. Currently, we're about 75 light-years above the mid-plane of the disk and moving upward. We'll continue rising for another 14 million years until we reach a maximum height of about 230 light-years above the plane. Then we'll fall back down, crossing through the midplane and descending to a similar distance below it before rising again. This oscillation takes about 64 million years to complete, adding another rhythm to our orbit around the galaxy's center. The galaxy's hidden depths. The Milky Way is home to numerous stellar remnants, the ghostly remains of stars that have reached the end of their lives. Scattered throughout the galaxy are an estimated 100 million white dwarfs, the dense cooling cores of stars like our Sun that have shed their outer layers. There are perhaps 100 million neutron stars, the collapsed cores of massive stars compressed to incredible densities where a teaspoon of matter would weigh as much as a mountain. And hidden in the darkness are an estimated 100 million stellar mass black holes, the ultimate endpoints of the most massive stars, objects so dense that not even light can escape their gravitational pull. The galactic bulge at the center of the Milky Way is shaped somewhat like a peanut or an elongated box when viewed from certain angles. This unusual shape is the result of the central bar's influence over billions of years. As the bar rotates, it creates complex orbital patterns that cause stars to pile up in certain regions, sculpting the bulge into this distinctive three-dimensional structure. The bulge contains some of the galaxy's oldest stars, many formed over 10 billion years ago when the Milky Way was still young. Cosmic rays, high-energy particles that constantly bombard Earth from space, originate throughout the Milky Way. These particles, mostly protons and atomic nuclei traveling at nearly the speed of light, are accelerated by supernova shockwaves, pulsar winds, and other violent events scattered across the galaxy. Every second, several cosmic rays pass through your body, having journeyed for thousands or millions of years through interstellar space before reaching Earth. The Milky Way acts as a cosmic particle accelerator, filling the space between stars with these energetic wanderers. The rotation curve of the Milky Way remains flat far beyond the visible edge of the galaxy, meaning that stars and gas in the outermost regions orbit just as fast as those closer in. This unexpected behavior is one of the strongest pieces of evidence for dark matter. According to our understanding of gravity based on visible matter alone, the rotation speed should drop off significantly in the outer regions, but it doesn't. This tells us that an enormous halo of invisible dark matter extends far beyond what we can see, its gravity keeping the outer regions moving at their observed speeds. Within the Milky Way exists a phenomenon known as the galactic fountain. Hot gas heated by supernovae and stellar winds in the disk rises high above the galactic plane, cools as it expands, and then falls back down like water in a fountain. This cycle helps regulate star formation, removes energy from the disk, and redistributes metals throughout different parts of the galaxy. It's a continuous circulation system that has been operating for billions of years, connecting the disk to the halo in an endless exchange of material. The Milky Way's central black hole, Sagittarius A, is remarkably quiet for a supermassive black hole. While it occasionally flares up when it captures a wayward gas cloud or star, most of the time it's relatively dormant. But evidence suggests it wasn't always this way. Studies of the Fermi-bubbles and other structures hint that just a few million years ago, the black hole was much more active, perhaps consuming material at a far higher rate and generating powerful jets of energy that carved out the giant bubbles we observe today. The concept of galactic recycling describes how material in the Milky Way is constantly being reused. Stars form from gas clouds, live their lives fusing hydrogen into heavier elements, and then return much of their mass to space through stellar winds or explosive deaths. This returned material, now enriched with heavy elements, mixes back into the interstellar medium where it can form new generations of stars and planets. Every atom in your body has likely been through multiple cycles of this cosmic recycling, forged in ancient stars, scattered through space, gathered into new clouds, and eventually incorporated into our solar system. The Milky Way contains numerous star streams, elongated groups of stars that share similar motions and compositions. These streams are the stretched-out remains of globular clusters or small galaxies that have been torn apart by the Milky Way's tidal forces. Like breadcrumbs marking a path through the forest, these stellar streams trace the orbits of their parent objects, allowing astronomers to map out the distribution of mass in the galaxy and understand its gravitational structure. More than 60 such streams have been identified, each one a fossil record of a cluster or galaxy that was absorbed by the Milky Way. The speed of sound in the interstellar medium is surprisingly fast, typically around 10 to 20 kilometers per second, much faster than sound in Earth's atmosphere. This is because temperature, not density, primarily determines the speed of sound, and the interstellar medium, though incredibly thin, can be quite hot in regions heated by stars and supernovae. Shockwaves from exploding stars travel through this medium faster than sound, creating both shocks and other structures that compress and heat the gas, triggering new waves of star formation in a chain reaction that propagates through the galaxy. The Milky Way will eventually run out of gas to form new stars, but that distant future is still billions of years away. Currently, the galaxy is converting its gas into stars slowly enough that it has fuel remaining for perhaps another 5 billion years or more of star formation. However, this timeline will be dramatically altered by the galaxy's upcoming collision with Andromeda. When these two galaxies merge, the gravitational interactions will compress enormous amounts of gas, likely triggering a spectacular starburst that could consume much of the remaining fuel in a relatively brief cosmic fireworks display. Celestial timekeepers. The Milky Way's spiral structure is not permanent but rather a dynamic pattern that has likely changed significantly over the galaxy's lifetime. Computer simulations suggest that the number and shape of spiral arms can vary over time, influenced by gravitational interactions with satellite galaxies, density waves propagating through the disk, and the effects of the central bar. What we see today is just one snapshot in a continuously evolving galactic portrait, a pattern that has shifted and reformed countless times over billions of years. Pulsars, rapidly spinning neutron stars that emit beams of radiation like cosmic lighthouses, serve as some of the most precise clocks in the universe. The Milky Way contains thousands of known pulsars, and they're distributed throughout the galaxy in ways that help us understand stellar evolution and the structure of the interstellar medium. Some pulsars spin hundreds of times per second with such regularity that they rival atomic clocks in their precision. By timing the arrival of pulsar signals, astronomers can even detect the subtle ripples in spacetime called gravitational waves. The metallicity gradient in the Milky Way's disk shows that the inner regions are more metal-rich than the outer regions. This radial gradient exists because star formation has been more intense and sustained in the inner disk over the galaxy's history, leading to more generations of stars enriching the gas with heavy elements. The gradient provides important clues about how the disk formed, supporting models where the galaxy built itself from the inside out, with the inner regions forming first and the outer disk assembling more gradually over time. Our galaxy contains enormous structures called superbubbles, vast cavities blown out of the interstellar medium by the combined effects of multiple supernovae and powerful stellar winds from clusters of massive stars. These superbubbles can be hundreds of light-years across, filled with million-degree gas that glows in X-rays. They represent regions where stellar feedback is so intense that it has essentially cleared out most of the gas, creating huge voids surrounded by dense shells of compressed material where new stars may eventually form. The vertical distribution of stars in the Milky Way's disk follows a pattern described by what astronomers call the scale height. For the thin disk, this scale height is about 300 light-years, meaning that the density of young stars drops by about half for every 300 light-years you move above or below the galactic plane. Older stars have a larger scale height, typically around 1,000 light-years, because over time, gravitational interactions with molecular clouds and other stars gradually increase the random vertical motions of stars, causing the disk to thicken as it ages. The Milky Way's total luminosity, the amount of light it emits across all wavelengths, is approximately 25 billion times the luminosity of our Sun. Despite containing hundreds of billions of stars, many are dim red dwarfs that contribute relatively little light. Most of the galaxy's visible light comes from a much smaller population of bright, massive stars. If you could somehow gather all the starlight from every star in the galaxy and focus it into a single point, it would outshine our Sun by this enormous factor. Within the galaxy, there exists a population of stars called high-velocity stars, which move through the Milky Way at speeds significantly different from the typical orbital velocities of stars in their neighborhood. These stellar mavericks may be old stars from the galactic halo passing through the disk, stars kicked to high speeds by gravitational encounters, or immigrants from disrupted satellite galaxies. Their unusual motions make them stand out like speeders on a highway, and studying them helps astronomers understand the full range of stellar dynamics in our galaxy. The Milky Way's spiral arms are not empty of stars between them. Rather, the arms represent regions of enhanced stellar density where stars are more concentrated. Think of them like traffic jams on a circular highway. Cars move through the jam, slowing down and bunching up in the congested area before accelerating again once they're through. Similarly, stars and gas clouds move into and out of the spiral arms as they orbit, spending more time in the denser regions where they slow down slightly due to the increased gravitational pull. The galaxy experiences what astronomers call self-gravity, meaning the collective gravitational pull of all its constituent parts, stars, gas, and dark matter, holds the structure together. No external force is needed to keep the Milky Way intact. It's a self-organized, gravitationally bound system where every piece of matter influences every other piece. This self-gravity is what allows spiral patterns to form and persist, what keeps the disk flat, and what maintains the intricate balance between the various components of our galactic home. Recent observations have revealed that the Milky Way's disk has a slight ripple or corrugation pattern, waves in the vertical structure of the disk that extend across thousands of light-years. These ripples may have been caused by a small satellite galaxy passing through the disk sometime in the last few 100 million years, like a stone thrown into a pond creating expanding waves. The ripples are gradually damping out, but they provide evidence of relatively recent gravitational disturbances that have affected our galactic neighborhood. The Dance of Giants. The upcoming collision between the Milky Way and the Andromeda Galaxy, predicted to occur in approximately 4.5 billion years, will be a slow-motion cosmic ballet lasting billions of years. Despite containing hundreds of billions of stars combined, the vast distances between individual stars mean that direct stellar collisions will be extraordinarily rare. Instead, the galaxies will pass through each other, their shapes distorted by mutual gravitational forces, before falling back together and eventually merging into a single giant elliptical galaxy that astronomers have playfully nicknamed Milkomeda or Milkdromeda. The Milky Way's halo contains streams of stars with very unusual compositions and orbital characteristics that reveal the galaxy's violent past. The largest of these, discovered by the Gaia Space Telescope, includes stars that were once part of other galaxies now long destroyed. Each stream is like a fossil, preserving information about ancient merger events. By studying the chemistry and motions of these halo stars, astronomers can reconstruct a timeline of the Milky Way's growth, revealing which galaxies it consumed and when. Our galaxy rotates in what we call a clockwise direction when viewed from the North Galactic Pole, above the galactic plane. But this is merely a convention, a perspective chosen by astronomers. From the opposite side, from the South Galactic Pole, the rotation would appear counterclockwise. What matters is that this rotation is incredibly slow from our human perspective. Despite our solar system traveling at over 500,000 miles per hour, we've only completed about 20 orbits around the galaxy since the Milky Way formed, a leisurely 20 laps around the cosmic racetrack in more than 13 billion years. The Milky Way contains numerous planetary nebulae, the beautiful glowing shells of gas ejected by dying sun-like stars in their final stages of evolution. These nebulae, despite their name, have nothing to do with planets. They were named by early astronomers who thought their round, disc-like appearance through primitive telescopes resembled planets. The galaxy may contain tens of thousands of planetary nebulae at any given time, each one marking the transformation of a red giant into a white dwarf, each one returning precious elements to the interstellar medium to be recycled into future generations of stars. The mass of Sagittarius A*, our galactic center's supermassive black hole, has been measured with remarkable precision by tracking the orbits of stars that whip around it at tremendous speeds. One star, designated S2, completes an orbit around the black hole in just 16 years, coming as close as 120 astronomical units at its nearest approach. That's only about 4 times the distance of Neptune from our Sun. Yet S2 reaches speeds of nearly 3% the speed of light during its closest approach. By carefully measuring such stellar orbits, astronomers determined that Sagittarius A* contains 4.15 million solar masses compressed into a region smaller than Mercury's orbit. Throughout the Milky Way, there are regions called HII regions, pronounced H2, which are vast clouds of ionized hydrogen gas glowing with the energy of hot, young stars embedded within them. These emission nebulae, like the famous Orion Nebula, are stellar nurseries where massive stars have recently ignited, their intense ultraviolet radiation stripping electrons from surrounding hydrogen atoms and causing the gas to fluoresce in shades of red and pink. The galaxy contains thousands of these glowing beacons marking the locations of recent star formation. The average density of matter in the Milky Way's disk in our solar neighborhood is remarkably low, roughly equivalent to about 1 hydrogen atom per cubic centimeter. Yet this is actually quite dense compared to the intergalactic medium beyond our galaxy, where you might find only 1 atom per cubic meter or less. In the molecular clouds where stars form, densities can reach millions of particles per cubic centimeter, while in the thin hot halo, the density drops to a tiny fraction of a particle per cubic centimeter. The galaxy is thus a place of enormous contrasts, from nearly perfect vacuum to relatively dense stellar nurseries. Binary and multiple star systems are extremely common in the Milky Way. Approximately half of all Sun-like stars exist in binary systems, orbiting a companion star, and many stars are part of triple or even more complex multiple star systems. This means that if you were born on a planet orbiting a star elsewhere in the galaxy, you'd have roughly a 50% chance of seeing 2 or more suns in your sky. Our solar system, with its single star, may actually be in the minority, a lone sun in a galaxy filled with stellar partnerships and families. The Milky Way's rotation period varies with distance from the center, but in our solar neighborhood, stars take approximately 225 to 250 million years to complete one orbit. This period is sometimes called a cosmic year or galactic year. Since the formation of our solar system 4.6 billion years ago, Earth has completed roughly 20 cosmic years. To put this in perspective, the last time our solar system was in its current position relative to the galaxy, the supercontinent Pangaea was beginning to break apart, and the age of dinosaurs was in full swing. Within the galactic bulge, there exists a distinct population of stars that are unusually rich in heavy elements, even more so than the Sun. This overabundance of metals suggests that the central regions of the galaxy underwent rapid and intense star formation early in cosmic history, with many generations of massive stars living fast, dying young in supernovae, and quickly enriching the gas with heavy elements. The bulge represents the oldest and most chemically evolved part of the Milky Way, a cosmic furnace where elements were forged in the galaxy's turbulent youth. Rivers of stars. The Milky Way is surrounded by about 60 known satellite galaxies, small companion galaxies held in orbit by the Milky Way's immense gravitational pull. The largest and brightest of these are the Magellanic Clouds, but most are dwarf spheroidal galaxies so faint they're incredibly difficult to detect. These tiny galaxies contain anywhere from a few thousand to a few million stars, compared to our galaxy's hundreds of billions. Many of these satellites are being slowly stripped of their stars and will eventually be completely absorbed into the Milky Way, adding their stellar populations to our galactic family. The concept of stellar populations extends beyond just age. Population 1 stars are not only younger but also follow more circular orbits in the galactic disk, while population 2 stars have more eccentric, elongated orbits that can take them far above and below the plane. This difference in orbital behavior reflects their origins. Population 1 stars were born in the settled, rotating disk where gas had time to organize into a flattened structure. Population 2 stars formed earlier, when the galaxy was more chaotic and hadn't yet settled into its current orderly rotation. Dark matter in the Milky Way isn't concentrated in the visible disk but instead forms a roughly spherical halo that extends perhaps 600,000 light-years from the galactic center, far beyond any visible stars. This dark matter halo contains most of the galaxy's mass and creates the gravitational scaffolding that holds everything together. Without it, the galaxy as we know it couldn't exist. The visible matter, all the stars and gas we can see, is essentially embedded in this vast invisible cloud like raisins in a pudding, tracing the gravitational contours created by the dark matter. The Milky Way has a relatively low rate of star formation compared to some other galaxies in the universe. While we create about 3 solar masses of new stars per year, some starburst galaxies can form hundreds or even thousands of solar masses worth of stars annually. Our galaxy is what astronomers consider a normal spiral galaxy, forming stars at a steady, moderate pace that can be sustained for billions of years. This leisurely pace may actually be beneficial for the development of life, as it means fewer disruptive supernovae and a more stable galactic environment. Throughout the galaxy, stellar winds from hot, massive stars and gentle breezes from dying sun-like stars continuously blow material into space. These winds, combined with supernova explosions, create a complex circulation system within the galaxy. Hot gas rises into the halo, cools, and falls back down, while fresh gas from intergalactic space slowly accretes onto the galaxy's outer edges. This ongoing flow of material means the Milky Way is not a closed system but rather exchanges matter with its surroundings, breathing in and out like a living organism. The Orion Arm, where our solar system resides, is sometimes called a spur or a branch because it's smaller and less prominent than the major spiral arms like Perseus and Sagittarius. It's about 10,000 light-years long and approximately 3,500 light-years wide. Despite being a minor feature in the grand structure of the galaxy, it's anything but insignificant to us. This arm contains many of the bright stars visible in our night sky, including Betelgeuse, Rigel, and the stars of the Orion constellation that give the arm its name. The Milky Way contains vast amounts of dust, tiny solid particles ranging from the size of molecules to grains about a micrometer across. This cosmic dust makes up only about 1% of the interstellar medium's mass, but it has an outsized impact on our view of the galaxy. Dust absorbs and scatters light, particularly blue light, which is why dusty regions can appear reddish and why we can't see through to the galactic center in visible light. This dust is crucial for star formation, providing surfaces where molecules can form and shielding the interior of molecular clouds from disruptive radiation. The Milky Way's thin disk shows a remarkable degree of organization. Not only do stars orbit in roughly the same plane, but they also orbit in the same direction, like cars on a circular highway all going the same way. This organized motion is a result of the conservation of angular momentum from the rotating cloud of gas that originally collapsed to form the galaxy. Any random motions have been gradually smoothed out over billions of years, leaving the orderly rotation we observe today. It's this rotation that gives spiral galaxies their characteristic flattened shape. Within our galaxy, there are stellar associations, loose groupings of young stars that were born together but aren't tightly bound by gravity like star clusters. These associations gradually disperse over tens of millions of years as their member stars drift apart. The nearest stellar association to us is the Scorpio-Centaurus association, located about 380 to 470 light-years away and containing thousands of young stars, including several that are visible to the naked eye. These associations represent recent star formation events, cosmic baby pictures showing us where stellar nurseries were active in the relatively recent past. The metallicity of the Milky Way's stars allows astronomers to determine their approximate ages through a technique called stellar archaeology. Older stars, born when the galaxy was young and hadn't yet been enriched with heavy elements from many generations of supernovae, have lower metallicity. Younger stars, born from gas that's been enriched by billions of years of stellar processing, have higher metallicity. By measuring the chemical composition of stars, astronomers can estimate when they formed and reconstruct the timeline of the galaxy's chemical evolution, reading the history of the Milky Way written in starlight. The final journey. The Milky Way contains numerous Wolf-Rayet stars, extremely hot and luminous stars that have blown away their outer hydrogen layers, revealing their helium-rich cores. These rare stellar giants, with surface temperatures exceeding 25,000 degrees Celsius, shed mass through powerful stellar winds traveling at thousands of kilometers per second. Only a few hundred Wolf-Rayet stars are known in our galaxy, and they represent a brief but spectacular phase in the life of the most massive stars, the last stage before they explode as supernovae and enrich the galaxy with freshly forged heavy elements. The local bubble is a cavity in the interstellar medium approximately 1,000 light-years across, within which our solar system currently resides. This bubble was carved out by supernova explosions over the past 10 to 20 million years, clearing away much of the gas and dust in our cosmic neighborhood. The bubble's walls, where the expanding blast waves have compressed the surrounding material, may be sites of ongoing star formation. We're fortunate to live in this relatively empty region, as the low density of material around us means less obscuration when we look out into the galaxy. The Milky Way experiences what astronomers call radial migration, where stars can gradually move inward or outward from their birthplaces over billions of years. This happens through gravitational interactions with spiral arms, molecular clouds, and other structures. Our Sun, for instance, may not have formed at its current distance from the galactic center but could have migrated here over the course of its 4.6 billion-year lifetime. This means that the chemical composition of a star doesn't always tell us where it was born, adding complexity to our understanding of galactic evolution. Within the galaxy, there are objects called microquasars, stellar mass black holes that are actively feeding on material from a companion star and producing jets of matter traveling at nearly the speed of light. These systems are miniature versions of the supermassive black holes and jets found at the centers of active galaxies. The Milky Way contains several known microquasars, and they provide astronomers with nearby laboratories for studying the extreme physics of black holes and relativistic jets without having to peer billions of light-years into the distant universe. The galactic disk is threaded with magnetic field lines that follow the spiral structure, creating a large-scale magnetic field pattern that spirals outward from the center like water flowing down a drain. This field, though incredibly weak by everyday standards, plays a crucial role in the dynamics of the interstellar medium, influencing how gas flows, how cosmic rays propagate, and how molecular clouds collapse to form stars. The magnetic field is frozen into the plasma of the interstellar medium, meaning the field lines move with the gas, creating a complex interplay between magnetic forces and gravity. Tidal streams from disrupted globular clusters crisscross the Milky Way's halo like cosmic spiderwebs. These streams are the elongated remnants of star clusters that have been pulled apart by the galaxy's tidal forces as they orbited through it. The most famous is the Palomar 5 stream, stretching across more than 20 degrees of sky. These tidal streams are incredibly useful to astronomers because they trace the gravitational potential of the galaxy, helping map out where mass, including dark matter, is distributed throughout the halo. The Milky Way's rotation creates a phenomenon called frame dragging near the supermassive black hole at the galactic center. This is a prediction of Einstein's general relativity where the rotation of a massive object literally drags space-time around with it. While this effect is incredibly subtle, astronomers have detected evidence of frame dragging by carefully tracking the orbits of stars near Sagittarius A star. The black hole's spin twists the very fabric of space and time around it, causing the orbital planes of nearby objects to slowly precess. Our galaxy contains numerous high-mass X-ray binaries, systems where a neutron star or black hole is pulling material from a massive companion star. As this material spirals inward, it heats up to millions of degrees and emits powerful X-rays. These systems are stellar laboratories where matter is pushed to extremes, allowing astronomers to study physics under conditions that can never be replicated on Earth. The Milky Way hosts dozens of known X-ray binaries, each one a cosmic accelerator producing some of the highest energy radiation in the galaxy. The concept of the co-rotation radius describes a special distance from the galactic center where stars orbit at the same speed as the spiral density waves. At this radius, stars and the spiral pattern move together, meaning stars remain in the spiral arms rather than moving through them. Our solar system is thought to be near this co-rotation radius, which may have been beneficial for the development of life on Earth. Being near co-rotation means we spend more time in the relatively empty space between spiral arms, away from the intense radiation and frequent supernovae found within the arms themselves. Hypervelocity stars, discovered in the early 2000s, are stars moving so fast they will eventually escape the galaxy entirely. Most of these stars were likely accelerated to their tremendous speeds through close encounters with the supermassive black hole at the galactic center, where the intense gravity can slingshot stars to velocities exceeding 1,000 kilometers per second. A few hundred candidate hypervelocity stars have been identified, each one on a one-way journey out of the Milky Way, destined to spend eternity wandering through the vast darkness of intergalactic space. The Milky Way's future is intimately tied to the fate of the local group. Over tens of billions of years, the mutual gravitational attraction between the Milky Way, Andromeda, and their smaller companions will cause most of the group's galaxies to eventually merge into a single massive elliptical galaxy. This megagalaxy will then slowly evolve in increasing isolation as the expansion of the universe carries other galaxy groups farther and farther away, eventually leaving our merged galaxy alone in an expanding cosmic void. Throughout our journey across 100 facts, we've explored the Milky Way from the dance of individual stars to the grand architecture of spiral arms, from the violent forge of the galactic center to the quiet suburbs where our solar system makes its home. The Milky Way is ancient yet still forming new stars, massive yet held together by invisible dark matter, orderly in its rotation yet scarred by collisions with smaller galaxies. The Milky Way contains somewhere between 100 billion and 400 billion planets, based on recent discoveries of exoplanets and statistical estimates. Nearly every star hosts at least one planet, and many have multiple worlds. Among these hundreds of billions of planets, there are likely billions in the habitable zones of their stars, where conditions might be right for liquid water and possibly life. We live in a galaxy teeming with worlds, most of which remain unexplored and unknown, each one a unique experiment in planetary formation and evolution. Perhaps one of the most profound facts is this: we are made of the Milky Way. Every atom in your body, except for hydrogen, was forged in the core of a star that lived and died somewhere in this galaxy before our solar system formed. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it was created through nuclear fusion in stellar furnaces and scattered through space by supernovae. We are, quite literally, made of stardust, temporary arrangements of atoms that the galaxy has assembled, granted consciousness, and given the ability to look up and wonder about our cosmic home. As we've seen through these 100 facts, the Milky Way is not just a collection of stars and gas, not just a structure defined by physics and chemistry. It is a vast ecosystem of matter and energy, a cosmic community where stars are born, live, and die, where elements are forged and scattered, where gravity and motion create patterns of stunning beauty. It is dynamic, evolving, and interconnected in ways we're only beginning to understand. The Milky Way has existed for most of the universe's history, and it will continue evolving for billions of years to come. Stars will be born and die, the spiral arms will slowly shift, satellite galaxies will be absorbed, and eventually, the great merger with Andromeda will transform our galactic home into something new. But for now, on this small blue world orbiting an average star in a minor spiral arm, we have the privilege of looking up at the night sky and seeing the galaxy from the inside, a band of light that connects us to the cosmic tapestry of which we are a part. Our journey through 100 facts about the Milky Way comes to an end, but the galaxy's story continues. Each night, it wheels overhead, a river of light containing more stars than we could count in 1,000 lifetimes, more worlds than we could ever visit, more mysteries than we could ever solve. Yet we keep looking, keep wondering, keep discovering new details about this magnificent spiral of stars we call home. The Milky Way is our address in the universe, our cosmic neighborhood, the galaxy that gave birth to the sun and earth and everything we've ever known. It's a reminder of our place in the vastness of space and time, a humbling perspective that we are part of something far grander than ourselves. And yet, remarkably, we are also the way the Milky Way has become conscious of itself, the means by which the universe can look back upon its own creation and marvel at its own beauty. So tonight, if the sky is clear, step outside and look up. Find that misty band of light stretching across the darkness. Remember that you're looking at hundreds of billions of distant suns, at vast clouds of gas and dust, at the spiral arms of a galaxy that has been turning for over 13 billion years. Remember that you are made of its ancient stars, that you are woven from the very fabric of the cosmos. The Milky Way is more than our home. It is our origin, our context, and perhaps, in some poetic sense, our destiny. And though we may be small and our lives brief in cosmic terms, we are part of this grand galactic story, participants in an ongoing saga that began billions of years ago and will continue for billions more to come. Thank you for joining me on this journey through 100 facts about the Milky Way. May you never look at the night sky the same way again. Here's a fact about cat hearing that adds to our understanding of their acute senses. Cats can rotate each ear independently up to 180 degrees, and they can move both ears in different directions simultaneously. This allows them to monitor two different sound sources at once without moving their head. Imagine being able to listen to a conversation on your left while also tracking footsteps approaching from your right. That's the acoustic world cats inhabit constantly. Those 32 muscles in each ear aren't just for show. They're precision instruments that give cats a three-dimensional audio map of everything happening around them, near and far. Let's explore something about cat personality that research has revealed. Scientists have identified 5 major personality dimensions in cats, often called the feline 5. These are skittishness, outgoingness, dominance, spontaneity, and friendliness. Just like humans have different personality types, cats display consistent individual differences in behavior and temperament. Some cats are bold explorers, while others are cautious observers. Some are social butterflies, while others prefer solitude. Understanding that these differences are part of your cat's inherent personality, not stubbornness or behavioral problems, helps us appreciate each cat as an individual and adjust our expectations accordingly. Your shy cat isn't being difficult, they're simply being themselves. Now, here's something about cat reproduction that's quite remarkable. A single litter of kittens can have multiple fathers, as we discussed earlier, but here's an additional detail. Female cats can become pregnant again while still nursing a previous litter. This is called superfetation, though it's quite rare. More commonly, female cats can go into heat again very shortly after giving birth, sometimes within just a few weeks. This remarkable fertility is an evolutionary adaptation that allowed wild cat populations to recover quickly from losses. It's also why spaying is so important for population control. Unspayed female cats can theoretically produce multiple litters per year, contributing to overpopulation problems. Here's a fascinating fact about how cats drink milk, or rather, why adult cats shouldn't. Kittens produce an enzyme called lactase that allows them to digest the lactose in their mother's milk. However, once weaned, many cats lose this ability, becoming lactose intolerant. Giving adult cats cow's milk can lead to digestive upset, diarrhea, and discomfort. Despite the popular image of cats lapping up sources of milk, water is actually the best beverage for adult cats. That said, some cats retain the ability to digest lactose into adulthood, but it's better to err on the side of caution. The happy cat with a milk mustache is more myth than reality, or at least, it shouldn't be reality if we want our cats to feel their best. Let's turn to something about cat athleticism that's truly impressive. Cats have incredibly powerful hind legs relative to their body size. These legs can generate enough force to propel a cat upward to heights of 5 to 6 feet from a standing position. This vertical leap ability is crucial for both hunting and escaping predators. Watch a cat crouch before jumping. You'll see them calculating the distance, adjusting their position, and then exploding upward with remarkable precision. This jumping ability is powered by those fast twitch muscles we discussed earlier, working in perfect coordination with the cat's flexible spine and strong legs. It's a display of natural athleticism that would be equivalent to a human jumping over 30 feet straight up. Now, here's something about cat fur patterns that reveals beautiful complexity. The tabby pattern is actually the most common coat pattern in cats and exists in several variations: classic or blotched, mackerel or striped, spotted, and ticked. All of these patterns come from the same genetic blueprint, with small variations in gene expression creating the different looks. The characteristic M marking on a tabby cat's forehead appears in many cultures' folklore. Some say it stands for Mao, the Egyptian word for cat, while others tell stories of the Virgin Mary blessing a tabby cat that comforted baby Jesus. Whatever its origin, this marking is a genetic signature that appears in tabby cats worldwide, a common thread connecting cats across continents and centuries. Finally, let's consider something profound about the therapeutic effect of cats. Studies have shown that cat ownership can have significant health benefits for humans. The act of petting a cat can lower blood pressure and reduce stress hormones like cortisol. The presence of a cat can ease loneliness and provide emotional support during difficult times. Some research even suggests that children who grow up with cats have stronger immune systems and lower rates of allergies. Beyond these measurable benefits, there's something intangible about the companionship of a cat, the way they exist so fully in the present moment, their independence balanced with affection, their ability to be both wild and gentle. They teach us patience, respect for boundaries, and the value of quiet companionship. In caring for them, we often find that they're caring for us in ways we never expected. The final chapter, Living with Lions in Miniature. And now, as we arrive at our final facts, we'll discover how cats continue to weave themselves into the very fabric of human life. Let's begin with something that speaks to the global presence of cats. It's estimated that there are over 600 million domestic cats in the world today. They live on every continent except Antarctica, from bustling cities to remote villages, from tropical islands to Arctic regions. This remarkable distribution makes cats one of the most successful species on the planet, adapting to nearly every environment where humans have settled. Each one of these millions of cats is descended from those same wild cats who first approached human settlements 10,000 years ago, and yet each one is also an individual with their own personality, preferences, and quirks. Here's something about cat communication that we haven't yet explored. Cats communicate extensively through body language, and their pupils can tell you a lot about their emotional state. Dilated pupils can indicate excitement, fear, or arousal, essentially heightened emotion of any kind. Constricted, narrow pupils often suggest aggression or intense focus, though bright light will naturally cause pupils to narrow. Combined with other body language like ear position, tail movement, and posture, pupil size becomes part of a complex vocabulary. Your cat is constantly broadcasting their feelings through these subtle signals. Learning to read them transforms your relationship, allowing you to respond to your cat's needs before they escalate into stressed behavior. Now, let's talk about something that reveals cats' incredible adaptability. Cats are found in more households than dogs in many countries, including the United States. This popularity stems partly from their independence. Cats can be left alone during work hours more easily than dogs, they don't require walks, and they're generally quieter. But it's also about the unique quality of the human-cat relationship. Cats offer companionship without demanding constant attention, affection on their own terms, and a presence that's both comforting and unobtrusive. They fit into modern human lifestyles in ways that work for people living in apartments, working long hours, or simply preferring a more independent companion. Here's a fact about cat grooming that goes beyond what we've discussed. When cats groom each other, a behavior called allogrooming, they're doing more than cleaning. Allogrooming typically occurs between cats who have a close bond, and it serves to strengthen social relationships and establish trust. Cats usually groom areas that are difficult for a cat to reach themselves, like the top of the head and behind the ears. If your cat licks your hair or face, they're including you in their social group and grooming you the way they would a feline friend. It's one of the highest honors a cat can bestow. You're not just tolerated, you're family. Let's explore something about cat sleep that adds depth to our earlier discussion. Cats experience sleep cycles similar to humans, alternating between light sleep and deep sleep. During light sleep, which lasts about 15 to 30 minutes, cats remain alert enough to wake quickly if needed. Their ears might swivel towards sounds, and they can spring into action instantly. Deep sleep, including REM sleep where dreaming occurs, lasts only about 5 minutes at a time. This pattern reflects their wild ancestry, where being deeply asleep for extended periods could be dangerous. Even in the safety of our homes, cats maintain this vigilant sleep pattern, one eye metaphorically open even in slumber. Now, here's something about cat cognition that demonstrates their problem-solving abilities. Cats understand the principle of cause and effect. They learn that pushing a glass off a counter will cause it to fall and make a sound. They understand that meowing at the door will eventually result in it opening. They recognize that certain behaviors from them produce predictable responses from their humans. This understanding allows them to manipulate their environment effectively. That accidental knocking of objects off tables? Your cat knows exactly what they're doing. They're either experimenting with physics, seeking attention, or perhaps both. Intelligence in cats often manifests as strategic thinking aimed at getting what they want. Here's a remarkable fact about cat genetics and breeding. The gene responsible for polydactyl cats, cats with extra toes, is a naturally occurring mutation. Normal cats have 18 toes total, 5 on each front paw, 4 on each back paw, but polydactyl cats can have up to 28 toes. This trait was particularly common among ship's cats, as sailors considered them lucky and valued their superior climbing and hunting abilities. The most famous polydactyl cats today are probably the descendants of Ernest Hemingway's cats at his Key West home, where approximately half the cats are polydactyl. These extra-toed cats are a reminder of the genetic diversity that exists within the feline species. Let's turn to something about the cat-human bond that's deeply touching. Cats grieve. When a companion cat or a beloved human dies, cats can show signs of grief, changes in appetite, increased vocalization, searching behavior, and withdrawal. They understand absence, they feel loss, and they go through a mourning process. This capacity for grief speaks to the depth of attachment cats form, contradicting the old stereotype of cats as emotionally detached. Your cat's bonds, to you, to other pets, to their home, run deep, even if they express these bonds differently than we might expect. Understanding this helps us support cats through transitions and losses in their lives. Now, here's something about cat vision that completes our understanding of how they see. While cats can't see fine detail as well as humans and have that limited color perception we discussed, they have a much wider field of view. Humans can see about 180 degrees, while cats can see about 200 degrees. This wider peripheral vision was crucial for detecting predators and prey approaching from the sides. It's another example of how every aspect of a cat's physiology is optimized for survival, sacrificing some detail and color perception in exchange for better motion detection, night vision, and a wider view of potential threats and opportunities. Here's a fact about cat territoriality that explains outdoor behavior. When outdoor cats establish territories, they often create a timeshare system to avoid conflict. Different cats will use the same pathways and areas at different times of day, marking their presence with scent and respecting the schedules of other cats. This temporal territory system allows multiple cats to coexist in the same space without constant fighting. Indoor cats can develop similar patterns, particularly in multi-cat households, where cats might take turns using favorite perches or rooms at different times. Understanding this helps explain why introducing new cats requires patience. You're not just introducing personalities, you're renegotiating an entire territorial and temporal map. Let's explore something about the variety of cat sounds that's particularly charming. Some cats are naturally more vocal than others, with certain breeds like Siamese being famously talkative. But beyond breed tendencies, cats learn to adjust their vocalizations based on what gets results with their particular humans. Some cats develop extensive vocabularies of different sounds for different requests, while others remain largely silent, communicating primarily through body language. There's no right or wrong, it's simply individual variation. If you have a chatty cat, embrace the conversation. If you have a quiet cat, learn to read their subtle signals. Both are communicating, they're just using different dialects. Now, here's something about cat whiskers we haven't fully covered. Cats also have whiskers above their eyes, called superciliary whiskers, which protect their eyes by triggering a blinking reflex when touched. Even a light brush against these whiskers causes the cat to blink, protecting the eye from debris or injury. Additionally, cats have whiskers on the backs of their front legs, called carpal whiskers, which help them gauge the position of captured prey. Every set of whiskers serves a specific purpose, making the entire whisker system a sophisticated network of sensory information gathering tools. Here's a fact about cat hydration that completes our earlier discussion. Cats evolved from desert-dwelling ancestors, which is why they're so efficient at concentrating their urine and extracting water from their food. Their kidneys can create urine that's significantly more concentrated than dog or human urine, allowing them to survive on less water. However, this efficiency comes with a vulnerability. Cats are prone to urinary and kidney problems, especially as they age. This is why hydration is so crucial for cats, and why many veterinarians recommend wet food, which can contain up to 80% water, helping cats meet their hydration needs through their food just as their wild ancestors did. Let's consider something about the future of cats and humans. As our world changes, the role of cats in human society continues to evolve. They're no longer primarily working animals keeping granaries free of rodents, though some cats still perform this service. Instead, they're companions, therapy animals, and family members. They're subjects of scientific research that helps us understand animal cognition, social behavior, and even human-animal bonds. They're internet celebrities bringing joy to millions. The relationship that began 10,000 years ago continues to adapt and deepen, reflecting both our changing world and the enduring needs that brought cats and humans together in the first place. Here's something philosophical to contemplate. Every cat alive today carries within them an unbroken thread connecting them to those first wild cats who approached human settlements. Through countless generations, through civilizations that rose and fell, through changes we can barely imagine, cats have persisted. They've adapted without fundamentally changing, maintained their essential nature while learning to live alongside us. In a world of constant change, cats represent continuity, a living connection to the ancient past, to nature, to something wild and untamed that still chooses to share our homes. Finally, let's end with perhaps the most important fact of all. Cats have an extraordinary ability to teach us about the present moment. They don't worry about tomorrow or regret yesterday. When a cat is in a sunbeam, they're fully in that sunbeam. When they play completely. When they rest without guilt or restlessness. In their company, we're invited to slow down, to notice small pleasures, to be fully present. This might be the greatest gift cats give us, not just companionship, not just affection, but a daily reminder of how to simply be. In a world that constantly demands our attention, our cats show us that sometimes the most important thing we can do is curl up in a comfortable spot and appreciate the warmth, the quiet, and the peace of this single moment. Conclusion. And so we've completed our journey through 100 facts about cats, from their ancient origins to their modern lives, from their remarkable physiology to their complex emotions, from their hunting instincts to their capacity for love. Each fact is a small window into understanding these creatures who share our homes and our hearts. Whether you live with a cat now, have loved cats in the past, or are simply fascinated by these remarkable animals, remember this: every cat is both typical and unique, both ancient and contemporary, both wild and domestic. They are small mysteries curled up on our couches, ambassadors from the natural world living in our very homes. Thank you for joining this exploration. May you look at every cat you meet, whether they're your own beloved companion or a stranger glimpsed through a window, with new appreciation for the extraordinary being they truly are.